In the last video, after I showed you what scalar multiplication of a vector looked like, I explained what the geometric interpretation of that scaling looked like on a graph in 2 dimensions and in 3 dimensions. And after I showed you how to add and subtract two vectors together, I showed you what the geometric interpretation of that looked like. It's a little harder to do that with the dot product. Instead, what I'm going to do this time is I'm going to show you a formula, and then I'm going to demonstrate on a graph kind of what that formula is telling us, and then I'll prove that formula. Here are two vectors. I'm going to call them u and v. Unless they're the same vector, these two vectors form an angle, and we're going to call that angle theta. There is a way using vector algebra and vector arithmetic to figure out what that angle is. Here's the formula. The cosine of theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Now, magnitudes are real numbers, they're scalars, right? So I'm taking a dot product here, which is a scalar, and I'm taking the product of two magnitudes, which is a scalar. So I'm going to get that the cosine of theta is some number. This is going to be a number. If I have specific vectors, u and v, if I know their component, the actual numbers in their components, then I can determine what angle theta is by taking the cosine inverse of this number here. Another way to write this formula is by multiplying both sides by the denominator of the fraction on the right-hand side, that product of two magnitudes. I can get u dotted with v is equal to the magnitude of u times the magnitude of v times the cosine of theta. So those are just two different ways to say the same thing here. This one focuses on if I know magnitudes and I know the theta, the angle theta, then I can determine what the dot product is that way. But equally, if I know what the dot product is, or if I can determine it, then I can figure out what the cosine is, and by using inverse trigonometry, I can figure out what that angle is. Using this version of our formula, I'm now going to prove that this is true. And this is primarily, again, just so that you can see what a proof looks like. When you prove something, you need to start with an assumption and make any arguments that you need to make based on that assumption and show that the logical sequence of events that must occur leads to the conclusion that you're trying to claim. So what we're going to do here is we're going to say, we're going to start with vectors u and v, and I'm actually going to draw them. I've kind of got a drawing of them up here. I'll just use this scale, this diagram here. And I'm going to figure out what the vector v minus u would look like. Now at this point, it may not be obvious why I need that, but it will become clear as we move along here. The vector v minus u will look something like this. I'm going to take vector, let's start with vector v. I'll take vector v and I'll make a copy of it. Put that down there for now. And then I'll take vector u and make a copy of that. And I'll stick that down here. If I wanted v plus u, I would just do this. But I want v minus u. So what I really need to do, I'm going to have to do this in parts, is I'm going to need to put the head of u going in this direction and pretend there's no arrowhead on this side. This is just the tail. So now what I want to do is take that vector u, negative u, the one that I've created with the white arrowhead, and move it so that the tail of that is at the tip of vector v. I'm going to have to do this in two steps because my program won't let me move the blue and the white at the same time, but bear with me. There goes the direction, that vector, and there's the vector itself. Okay, so that is now v minus u. And v minus u means take v, the green arrow, the green vector, and add to it negative u, the blue arrow, the one with the white head. And what that looks like is a new vector. And that is this vector here that starts at the tail of the first vector and goes towards the head of the second vector. So this vector right here, this yellow vector, is v minus u. I'm going to take that from here and I'm going to place it on my original sketch. See if I can get that in the right place. And I'll label it v minus u. All right, and with that, I'm going to erase the rest of my the work that I did down here, because all I really needed to do was figure out what v minus u looked like, and so I don't need this anymore. Eventually, you won't need that either, or you won't need it at all. The reason it was important just now is because with practice, I can say that what u minus v looks like is a vector going in this direction, and what v minus u looks like is a vector going in this direction. But until you've done that a bunch of times, it may not be obvious. I wanted you to see how I got the vector v minus u. Now what I have, though, is a triangle. It's not a right triangle, and I have an angle, and I have some of the information about the lengths of the sides of this triangle. This one has side length, the magnitude of vector u. This one has side length, the magnitude of vector v. And the third one has side length, the magnitude of the new vector, v minus u. Okay, so now I'm ready to start my proof. I'm going to use something that I hope you remember from trigonometry called the law of cosines. And I'll write that down over here to the side, and then I'll erase it later, but I want to establish and or remind you what it is. It says that the third side of a triangle squared, that length, is equal to the sum of the squares of the other two sides minus twice the product of the lengths of the two sides times the cosine of the angle. So remembering that the angle and the opposite side are the two letters that show up here. The length of the third side, the one opposite the one you're taking the cosine of, that's the one that goes here. And then the rest of the formula just plays out. I'm not going to try to prove this because you should have learned that and satisfied yourself that it was true back in your trigonometry class. But now what I'm going to do is I'm going to use that formula to write out the relationship between the pieces that I have here. Note that this is my angle, theta is my angle C in the equation here. The side opposite that is this v minus u vector's magnitude. It's the length of the side, so and I got it from this, the length of this vector here, the length of the side is the length of the vector v minus u, and the lengths of the other two sides are the magnitude of u and v, respectively. So, by the law of cosines, the magnitude of v minus u squared is equal to, now it doesn't matter which side I put A and which side I put as B, so I'm going to put them in alphabetical order in the same way as they are in the formula there. Doesn't really matter, but I'll go magnitude u squared plus magnitude v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. This next part gets a little hand wavy because it's just a little bit beyond our current understanding of dot products, but it does use the dot product. So I'm just going to kind of walk my way through it, and I don't want you to worry too much. If you don't quite follow, that's okay. I just want to convince you in the end that this formula actually exists and it really works. So I'm going to say that I'm going to make a note that the magnitude of vector v minus vector u squared can be written as the dot product v minus u dotted with v minus u. And I've used parentheses here rather than brackets because each of these things inside the parentheses is itself a vector. And I'm just using the parentheses to group the vectors. Without them, without the parentheses, I'd have v minus u dotted with v minus u. and this dot product would have to come first. That's not the same thing. So I've used the parentheses just to group them, group my vectors so that I don't make that mistake. And this, in turn, equals v minus u dotted with v minus v minus u dotted with u. Part of this is coming from something called the properties of the dot product, and we haven't got to that part yet. So the step that I just made here, the fact that I can go from here to here, is down to the dot product's properties, and we haven't actually talked about those yet, so try not to panic. We'll get to them eventually. That I can in turn write as v dotted with v minus u dotted with v. And from that, I can subtract v dotted with u. What I'm doing now is subtracting, that's this minus right here, subtracting v dotted with u, and then I'll subtract u dotted with u, but I'm subtracting a negative, so I'm going to have plus u. Oops, I forgot my v dotted with u. V dotted with u minus negative, if you will, u dotted with u. It's going to turn out, we're going to show later on, that vector multiplication, the dot product, is commutative. So that means that I can write this as uv or as vu. This one here. I'm going to change this one so that it's a u dotted with v. And if I do that, then I get v dotted with v minus u dotted with u dotted with v minus u dotted with v again. So I get minus 2 times u dotted with v. It's almost as though these were just variables. They are not, but at the moment they are behaving like variables. Oops, that's a u. Okay, and then of course I can write that. If I can do this, if I can write this product right here, this v minus u magnitude squared, as the dot product of two differences, then I can do the same in reverse. I can write this as the magnitude of v squared minus 2u, keep writing v when I mean u dotted with v plus the magnitude of u squared. Now, I can use this version. I can write this difference squared. This can be written as the dot product. It can be written this way, and it all comes down so that it looks like this. In other words, this thing right here, this magnitude v minus u squared, is equal to this other way of writing it. So what I'm going to do now is take this version of the law of cosines and substitute this. I'm going to highlight this. I'm going to substitute this version, or this way of writing this, in for this guy here. So that's going to go there. And that means every once in a while my pencil just stops working. This means we can write the law of cosines as magnitude v squared minus 2u dot v plus magnitude u squared. That's the equivalent of my left-hand side, right? I've used that. And the right-hand side I'll leave as it is. Magnitude u squared plus magnitude v squared minus 2 magnitude u magnitude v cosine of theta. Therefore, mathematicians are notoriously lazy. We like to write symbols when we, instead of a whole word, there's a shorter way to write it. Oftentimes you'll find this symbol here means therefore. Algebraically, let's see, I can take the term v squared away, magnitude of v squared, away from both the left-hand side and the right-hand side. And I can subtract the term, the magnitude of u, from the left-hand side and the right-hand side. And so what I've got left now is -2 vector u dotted with vector v equals -2 magnitude u times magnitude v times cosine of theta. And let's divide both sides by -2. Get rid of those. This is just a product. Now this -2 was times that, and it was also times that. So I've just divided both sides by -2. So now I have u dotted with v is equal to magnitude u times magnitude v times cosine of theta. And that's the end of the proof. And my point in doing this was to show you sort of the logical sequence of steps to get from a claim to a statement of some facts and show you how those things tie together, but also show you that while on one hand I might just record the explanation and sort of make a few notes, when you're writing a formal proof, you actually need to write out the words that, if you weren't watching this on a video, you would need to fill in the gaps between the steps. So that's something to keep in mind as you go forward in your mathematical career. When you're writing a proof, you have to be really quite explicit about what it is you're trying to say and actually say it. Rather than just a sequence of steps, you need to include any verbiage that sort of fills in the gaps. Well, that was fun, but let's see what this actually looks like in practice. If I have two vectors that are, say, 4 and 3 units long, let's see what we can do about finding the angle. Quite the opposite. Let's say we know the angle between these two vectors is theta equals 80 degrees. I can find out what the dot product of u with v is simply by finding the magnitude of u, or using what I've been told is the magnitude of u, multiplying it by the magnitude of v, and multiplying that by the cosine of theta. In this case, that's going to be 4 times 3 times the cosine of 80, which is 12. I'll have to get my calculator out because 80 is not a familiar angle. Cosine of 80 is, I just cleared it. The cosine of 80 is 0.174. Not exactly, of course. I've rounded that to 3 decimals. If I multiply that by 12, I get, should be approximate as well, actually. I get 2.084 if I round to 3 decimal places. So I can use the information about the magnitudes of the vectors and the angle, size of the angle between them to determine the dot product, but that's not actually how this is mostly used. How this information is mostly used is in that other form that we have of this, this formula, and that is that the cosine of theta is equal to the dot product of two vectors divided by the product of their magnitudes. Okay, so in this case, here I was using the form of the formula u dotted with v equals magnitude. Oh, I guess I have it here. Maybe I won't write that again because I had it already here. So that's that form of the formula. Here's the other form of the formula. And this is actually how we most commonly actually use this. If I have a vector u and a vector v, and I know that the vector u is, I'm going to use this angle bracket notation here just because it's a little bit less cumbersome. Let's call that, let's say that's negative 2, 2. And we'll say vector v looks like about maybe 3, 1. Then I can find the angle between these two vectors, if I call it theta, by using this formula here. So let's just dive in here. The cosine of theta is going to be equal to the dot product of u with v divided by the magnitude of u times the magnitude of v. The magnitude of u is negative 2 squared plus 2 squared under the square root, and v is 3 squared plus 1 squared under the square root. And I'll do that arithmetic now. Remember, a dot product is just this negative 2 times the first components, the product of the first components. That's going to be negative 2 times 3, added to the product of the second two components, added to, if there's a third component, the product of those, and so on. In this case, it's just a two-dimensional vector, so there are only two components. Divided by, and u is going to have the magnitude. This is going to be 4 plus 4, which is 8. That's the square root of 8. I'll just go ahead and leave it like that for now. And v has the magnitude, the square root of 9 plus 1, or 10. That is negative 6 plus 2, which is negative 4, over the square root of 8 can be written as 2 root 2, and the square root of 10 can be written as the square root of 2 times 5. I can combine these two to get another 2 out, and I have negative 4 over 4 root 5, or negative 1 over root 5. And that, ladies and gentlemen, is the cosine of theta. So theta is going to equal the arc cosine, or the inverse cosine, of negative 1 over root 5. And I'll take to my calculator to do that. I'm going to go into radians for this one just because I know I can trust that. Plus, it's much more common in actual applications. Second cosine, and I want negative 1 over the square root of 5. And I get a decimal approximation of 2.034. 0.034 radians. And I need to look now carefully at my diagram because I want to make sure that this actually makes sense. Is this 2 radians worth of an angle? Have I gone into the wrong quadrant? Have I used the cosine inverse incorrectly? We can start to answer that question by recalling that cosine, I can talk about cosine inverse in quadrants 1 and 2. So I have to be in this region here to talk about cosine inverse. And in terms of radians, and I'm at 2 radians here, in terms of radians, if I go from 0 degrees to 90 degrees to 180 degrees, that's pi radians, which is a little over 3. If I go all the way around, that's 2 pi, which is a bit over 6. So all the way between here and here is about 3 radians. And I'm saying that the angle that I've just found is a little bit, well, really right on about 2/3 of that. So about there. I'm saying theta is about that size. Now, it doesn't really look like it in this diagram. My angle's a little off, and that's partly because I drew the vectors first, and then I claimed that they were vector -2, 2 and vector 3, 1, and that's probably not very accurate. So my point really is that having found a vector, sorry, having found an angle, I have just verified that I have found an angle that works to answer this question, because it is, in fact, having found it using cosine inverse, it is, in fact, in the right realm. It's in the first two quadrants, which is where I'm allowed to play with cosine inverse. So this is actually a much more common use of these formulas than the first one that we did. This last bit is a little bit less than critical, but I do want to just show you. First of all, I think I'll take a moment and remind us that we can do this thing called a dot product with vectors in any dimension as long as the two vectors we're dotting have the same dimension. So let's use, let's go 1, 0, -1 for u, and let's go 2, 1, 0. I don't want to use too many zeros. Let's go with 2, 1, 1 for vector v. In 3 dimensions, that would look something like this. See, this is my x-axis, this is y, and this is z. And u is going to be starting at the origin. It's going to come out 1 in the x direction. It's not going to go out in the y direction at all. But then it's going to go down 1 in the z direction. So it's going to end right about there. That is vector u. Vector v goes out 2 in the x direction, goes to the right 1 in the y direction, and then it goes up 1 in the z direction. Let's see if I can erase some of that because it's a little bit confusing. So vector v ends there. Those are probably not the best vectors that I could have chosen to work with. But that's vector u and vector v. And if I want to find the angle between them, that angle right there, theta, all I need to do is say that cosine of theta is equal to the dot product of u with v divided by the product of the magnitudes of u and v. Well, the dot product of u and v is going to be 1 times 2 plus 0 times 1 plus -1 times 1. The magnitude of u is going to be 1 squared plus 0 squared plus -1 squared. And v has magnitude 2 squared plus 1 squared plus 1 squared, each under a square root. That gives me a numerator of 2 minus 1, which is 1, over, let's see, the square root of 1 squared plus 0 squared plus 1 squared is 2, so that's the square root of 2, times the square root of 4, 5, 6, square root of 6. 6 can be written as 2, root of 2 times 3. Goodness me. So I have 1 over root 2 times root 2 times 3, which is ultimately 1 over 2 root 3. So that is the cosine of theta. Therefore, theta equals cosine inverse of 1 over 2 times root 3. And I'll just stick that in my calculator. Cosine inverse of 1 over 2 root 3, which is approximately 1.278. radians. So the dot product is a pretty powerful tool. We could consider this finding the angle between two vectors an application of the dot product. So it's kind of nice to see an application. It seems like it's not really a real world application, but it is certainly a way in which the dot product is used. All right, now I'm going to take a look at a special case. Let's write this formula out again. U dotted with V equals the product of the magnitudes of U and V times the cosine of theta. And let's take a look at what happens when my two vectors, U and V, are at right angles to each other. In other words, theta is known to be pi over 2. Of course, that's 90 degrees if you're in degrees, but I'll be working in radians. If we know the angle here, then we can say that the dot product of U and V is equal to the magnitude of U times the magnitude of V times the cosine of pi over 2. What is the cosine of pi over 2? It's 0. So that would give us that U dotted with V is equal to some magnitudes that we may or may not know times 0. And this whole right-hand side here is going to be 0. So U dotted with V equals 0 happens when theta is pi over 2. As it turns out, it happens in the other direction as well. If I know theta is pi over 2, if I know I have a 90-degree angle between two vectors, then the dot product is going to be 0. But just as powerfully, perhaps even more powerfully, if the dot product is 0, I am guaranteed that the angle between those two vectors is 90 degrees or pi over 2 radians. That's pretty powerful stuff. This is another one of those if and only if statements. Sometimes you'll see it like this. Sometimes you'll see it written out, if and only if. If you actually pick this apart, it's saying that if the first side is true, the second side is true, and it's saying only if the second side is true, then the first side is true. It's a linguistic tool, but it's also a very specific mathematical, has a very specific mathematical meaning. If I know the dot product is 0, I don't need to do any more work. I know that the theta, the angle between the two vectors, U and V, that I know that angle is pi over 2. If I know the angle between the vectors is pi over 2 or 90 degrees, then I'm guaranteed to find out that the vectors, the dot product of the two vectors is 0. In this case, we say that U and V are orthogonal. It's just really another word that means perpendicular to each other. But it's a term that you'll hear in this context, in the context of this course, and in the context of anything that uses matrices, vectors specifically. Orthogonal is the term, the preferred term for two vectors that are perpendicular to one another. They are orthogonal. Here's how you can use this information. Let's take two vectors, maybe some different letters here. A equals 3, -1, and B equals 3, 9. All right, let's say I ask you to find theta. How would I write that? Find the angle between vector A and vector B. Well, I know I'm going to need the dot product at some point anyway, right? And I'll figure out what the dot product is, and then I'll divide by the product of the magnitudes. But let's just start with the dot product, and that's going to be A 3 times 3 plus -1 times 9. Well, that's 9 minus 9, and that's 0. So I'm done because the dot product is 0. I've got A and B here, not U and V. A dotted with B equals 0 means that theta equals pi over 2. I'm done. A is orthogonal to B. If I figured out what the magnitudes were, if I had gone to the trouble of doing that first, I would find, let's see, I'm going to write this version of the formula here. Cosine theta equals A dotted with B over magnitude A times magnitude B. And what I've just found is that this value right here is 0. So that would have been 0 over some product, right? It doesn't matter what the denominator is because it turns out that the numerator is 0. And because the numerator is 0, the cosine of theta is 0. And when the cosine of theta is 0, it's because the angle between the two vectors is 90 degrees. The cosine of 90 degrees, the cosine of pi over 2 is 0. That's how we get this result.